All right, let's take a look at a heating curve, and we're going to use this to do some of our calculations for the thermodynamics unit here. This is a heating curve for water, and we know that because we see some landmark regions on this graph. Let me just remind you that a heating curve generally shows how much heat is added on the x-axis, and then on the y-axis we have temperature. So moving up the graph represents an increase in temperature. We're starting pretty low here, and as we add heat, move to the right, it does cause the temperature to increase. Then we hit this place on the graph where even with extra heat, there's no increase in temperature. Then after that, additional heat causes a rise in temperature again before this flattens off at 100 degrees, and we have this flat region where more heat added does not equate to an increase in temperature. And then finally, in this last section, additional heat added moving to the right causes the temperature to increase again. So what's going on in this graph? In the first section, we see that ice, this is water anywhere below 0 degrees, heat is added to ice and the temperature of the ice increases. Eventually, we reach a portion on this graph where all of the ice is now at 0 degrees, so any additional heat, rather than increasing the temperature, goes into a process called fusion or melting. And we have a math calculation that we can use for this. When we get to that point, we're going to employ this equation that says Q equals M times H fusion. Sometimes you'll see that equation written Q equals M times L fusion, where L stands for the latent heat of fusion. When we get to the next section of the graph, we see there that represents water being heated. So at that point, we employ a different equation. So this equation, the equation for calculating heat, shows that heat is equal to the mass times the specific heat capacity for liquid water times the temperature change. Once we reach 100 degrees Celsius, at that point where all of the water has been heated and now we're boiling the water, or vaporization. And again, you'll see that equation written as Q equals M times L in some textbooks, L vape for the latent heat of vaporization. Or we'll be using an equation that says Q equals M times H vaporization, the heat of vaporization. And then once we finish vaporizing or boiling all of the water, that is to get it from a liquid to a vapor state or a gas, now that vapor or gas can continue to increase its temperature in this last portion where we're heating up steam. And again, we would employ the Q equals MC delta T equation for that. In order to do our calculations, we will need a list of those constants, the latent heat of fusion and vaporization at the top, and then the C values called the specific heat capacity. There's a different value depending on water, whether water is a liquid or in the solid state or in the gaseous state. So we'll make sure that we use the correct value for each of those. See if we can do a calculation that involves this heating curve. We're going to look at example 1 here. It says how much heat is required to raise the temperature of 725 grams of ice from minus 15 degrees to minus 12.5 degrees. All right, so it sounds like in this problem, we're somewhere in, probably down in this region here for the heating up the ice. And so that means we should use this equation here, Q equals M times C for ice times delta T. Let's write down some variables. What do we know here? Again, we're using Q equals M C for ice delta T. So let's see if we know any of those variables. The Q is the variable we're looking for. That's the unknown, how much heat. We do have the mass here, so we'll write that down. M is equal to 725 grams. Now, you'll notice when we solve these problems in physics, we often work them in kilograms. In fact, the specific heat for ice, the constant, if I look that up over here, the specific heat of ice was given as 2060. That's joules per kilogram degrees Celsius. All right, so joules, 2060 joules per kilogram. That means I'm going to need one of those conversions, one of those values there to be converted. And I think for me, I'll simply convert this one from grams to kilograms so that our mass is in kilograms and that we can cancel out those units. So to do this conversion, recall that a kilogram is equal to 1,000 grams. Dividing by 1,000 moves the decimal 3 places. We could write the mass as 0.725 kilograms. All right, the last two variables that we're going to use, we have the initial temperature given at minus 15 degrees Celsius, the final temperature at minus 12.5 degrees Celsius. And in our equation, we want delta T. So the delta T value can be calculated by taking the final minus the initial. Delta T is T final minus T initial. In other words, let's see, minus 12.5 degrees Celsius minus negative 15 degrees Celsius. So that's the same as saying minus 12.5 plus 15. And that would give me a positive 2.5 degrees Celsius. The temperature is increasing, so it has a positive sign. Take each of those values and plug them in to Q equals mc delta T, C for the ice. Q will equal 0.725 kilograms times 2,060 joules per kilogram and a degree Celsius. Delta T goes in as positive 2.5 degrees Celsius. Looks like we'll be able to cancel the kilograms and the degrees Celsius out of this. And so when we calculate the value for Q, should have the units of joules. Put those numbers in my calculator and I get 3,733.75 joules. Now we're going to write our answer with 2 sig figs, and we're doing that because of this measurement here. So I would call that 3,700 joules. That's a number you might want to convert. Large numbers sometimes we'll see written as kilojoules, so that could also be written as 3.7 kilojoules. Great. Let's look at another calculation. In this calculation, the question is a little bit different. How many kilograms of water at 100 degrees Celsius can be vaporized to steam at 100 degrees Celsius with 522 kilojoules of heat? So in this question, we're talking about water that's at 100 degrees Celsius being converted into steam. So we're somewhere along this part of the diagram where we're vaporizing water. And that's where we use this equation here. Q equals the mass of water times the heat of vaporization. All right, the equation again, Q, the heat, will equal the mass of the water times the heat for vaporizing the water. In order to do this, we're going to need, let's write down some numbers first. I'm going to write down the value for Q. So in this problem, they tell us Q, they tell us the heat is 522 kilojoules. 522 kilojoules. They're asking us to calculate M. M is what we don't know. We can look up H, vaporization. That is a constant. So in each of these equations, you'll find a constant. Having a table like this one is very useful. So this shows the constant for the heat of vaporization as 2.26 times 10 to the 6th joules per kilogram. Joules per kilogram. So I notice here that our heat was in kilojoules and our constant has joules in it. We need to convert one of these units again. I'm going to choose this one and write this as, let's see, 1,000 joules per kilojoule. So I don't really want to write this number out well. It's a lot of zeros to write. Sometimes we'll use scientific notation for our really large numbers, but I think in this case, I'll just go ahead and write it out this way. If I chose scientific notation, 5.22 times 10 to the, fifth power, and that makes it a little bit easier to write the number. In fact, let's put that down here. 5.22 times 10 to the 5th joules. All right, we grab our equation. Q equals M times H vaporization. Now in this equation, we're trying to find M. Recall that we could plug in numbers here, or we could just solve the equation for the missing variable. If you plug in numbers, there's a little more writing to do. So generally what I'm going to do is rearrange my equation first, solving it for M, that is divide both sides by H vape. And so M will equal Q divided by the heat of vaporization. And then I will plug in some numbers here. Q is 5.22 times 10 to the 5th joules. And the heat of vaporization, 2.26 times 10 to the 6th joules over kilograms. So what happens when we divide these units, the joules cancel out, and our units are going to be 1 over kilograms, which is equal to a kilogram. Take out your calculator, divide these numbers. Looks like we're going to get a pretty small number here. This one comes out to 0.230973. More digits than we need, so let's round that off. This is kilograms. So we could round that and say, let's see, we get 3 significant digits, so we'll say 231 kilograms. Also, a number you might convert, you could write this in grams, and it's a little bit easier to write. So either one of those looks like the correct answer. What we just calculated is with 522 kilojoules of heat, you could boil or vaporize 231 grams of water, assuming that it was at 100 degrees already. Okay, and the last example, this one's going to be a little bit more complicated. We're doing the same kind of thing here, but the water isn't at 100 degrees. In fact, this says how much energy is required. We're looking for Q to get 1.5 kilograms of water from 85 to 115 degrees. So there's a couple things that we have to do with our heat in this process. We're starting at 85. 85 would probably be somewhere around here. We're going to get that up to the boiling temperature. And then we're going to take that water and move it over. We're going to boil all of the water. And then up to 115. So then we've got to increase the temperature of the steam a little bit. And that means we've got to do 3 different processes. We've got to do this one and this one and this one, all 3. When you got multiple processes, it's kind of important that you keep them all straight. So I'm going to carefully write down each of these, starting with heating the water. Heating the water means that we're going to use this equation, Q equals MC for water, delta T. Now keep in mind we have water that's 85 degrees Celsius, and we need to get it up to the boiling temperature of 100 degrees Celsius. The mass of the water is given as 1.5 kilograms. The specific heat for water we look up in a table, and that value is right here. Looks like it's 4,180. 4,180. Those units were joules per kilogram, degrees Celsius. Delta T for this, that's the change in temperature, where we take the final temperature and subtract the initial temperature. For this part of our process, we are here somewhere, like at 85 degrees. We need to get it up to here, which is 100 degrees. So the final temperature 100, the initial temperature 85. Okay, that's a 15-degree increase in temperature. Be careful on these problems. Sometimes it's a little confusing because you may be tempted to use that number as the final temperature, but we'll get there. We have to break this into processes. Each process has its own equation, so we're just chunking off the heating water right here. And we'll calculate the heat, that's Q, for that part of the process by taking 1.5 kilograms times 4,180 joules per kilogram degree Celsius. And then the temperature change to get to the boiling temperature was 15 degrees Celsius. This will give us the first section of our heating process. Let me cross out a couple things to confirm that I did this correctly. Looks like I'm about to calculate the joules of heat, and I do that by multiplying these three numbers. And I'll write down the number as 94,050, and that's in joules. We'll round our numbers off in just a minute. Okay, that just heats the water up to 100 degrees. And the next thing we have to do is we have to boil the water or vaporize it. Boiling the water will require a different equation. So for boiling the water, that is this equation here. I'm going to use Q equals M times the heat of vaporization. And I'll need this heat of vaporization to do that calculation. Q equals the mass times the heat to vaporize the water. The mass hasn't changed. The mass is still 1.5 kilograms. The heat for vaporizing water, we used that before. That was 2.26 times 10 to the 6th joules per kilogram. And so for this calculation, we take the product of the two, 1.5 kilograms times 2.26 times 10 to the 6th. It looks like that is going to be the significant portion of the heating in this. Let's see what we get when we multiply these two. We will get units in joules, and 1.5 times 2.26 times 10 to the 6th is a large number. It's 3,390,000. Scientific notation would be useful there. Let's call that 3.39 times 10 to the 3/6 power of joules. So much more heat goes into boiling than just heating the water. Not quite done yet. We've got the water now all turned into steam. So all 1.5 kilograms of it were vaporized. But now we have to heat the steam up beyond that 100 degrees, and we can do that calculation over here. Recall that when you're heating water or when you're heating steam, it is equal to the mass times the specific heat capacity for that material times the temperature change. The mass is still 1.5 kilograms. The specific heat capacity for steam, we look that number up, and that number right here, 2,020 joules for every kilogram and degree Celsius. 2,020 joules per every kilogram and degree Celsius. And then the delta T for this, recall that we are at 100 degrees and that we want to get all the way up to 115 degrees in this problem. So our final temperature will be 115, and currently we have heated the water to 100. It is now in the form of steam at 100, and so the temperature change we need is another 15 degrees in the positive. So for this part of the calculation, we again can simply multiply these values, 1.5 kilograms times 2,020. Let's put this, the specific heat of steam, 2,020 joules per kilogram and degree Celsius times 15. Okay, so I substitute in each of the values into this equation here. And this gives me, let's multiply those, 1.5 times 2,020 times 15. Another 45,450 joules. All right, the question was, what is the total amount of heat required? So we're going to add up these numbers. Each of these numbers here represents heat for a portion of the process. The total heat then would be the sum just take that number and add it to my 3390000 and add that to 94,050. And the sum of those three values, Q total, I will call that, is, let's put that in scientific notation also. This is the number my calculator tells me. This would be a good time to round that number off. I'll keep 2 sig figs on account of my mass having 2 and also my temperature changes having 2 significant digits. So in scientific notation with 2 sig figs, that heat is 3.5 times 10 to the 6th power. 10 to the 6th power. Those units are joules. We could also write that in kilojoules. Sometimes we do that with larger amounts of heat, and that would simply mean divide by 1,000, or 3.5 times 10 to the 3rd kilojoules of heat. Either one of those answers works. All right, I hope this helps you do some of your calculating. We've got some calculations where we'll be looking at different portions of the phase diagram for water. Keep in mind this one works for water. We could do something similar with any other substance, so other metals and whatnot. They're obviously going to have different temperatures for the melting temperature and for the boiling temperature. But as far as the equations go, the equations will look the same. There are specific heat equations when the temperature is changing. And then we also have these equations that are useful for looking at how much energy is required for a phase change, whether that be fusion or vaporization. One other little point, this curve can be done in reverse. We can start with steam and we can remove heat. Heat is given off. And the removal of heat then would be correspond to cooling down the vapor. And then at this point that we had labeled boiling, if we did that in reverse, that would be condensing the vapor, condensation. And then we would cool that vapor back down to the freezing point, at which point we would go through the process of freezing, the opposite of melting, and then we could further chill down the solid. All right, I hope this helps you as you are working on some of your thermodynamics calculations.